Okay, guys, today what we're going to talk about today is three tests to see if series converge or not. The first one is the geometric test, which we've already talked about, and so we'll rehash again today. The nth term for divergence test, nth term test for divergence. And this one is not on your AP test this year. So you can fast forward through it when I talk about it, and your worksheet won't have any problems on it, but I wanted to talk about it because I think it's worth talking about, and it's not that hard to do, and it's used very often, not on this AP test, but on other AP tests. And then also the P-series test. Okay, so these are three tests that we'll be talking about today. Each one will help us to test, hey, does a series converge or does a series diverge? All right, so let's first talk about this geometric series test. We've already covered last time. We talked about if you have a geometric series, and here's a geometric series. This one is a geometric series where the common ratio is 1/2, okay? If your R, the absolute value of your R, is less than 1, then what we said was that the geometric series will converge. All right, and then we had another example, and what we said was each time we got the new term, this geometric series had a common ratio of 3/2, and this 3/2 is bigger than 1, okay? And when the common ratio is bigger than 1 or equal to 1, what we know is that the series diverges, meaning if you added, if you take the sequence of its partial sums, so this is a sequence of the partial sums, what will happen is that it will increase or decrease without bound, okay, if your R is greater than or equal to 1. But if your R is less than 1, then what we have is the geometric series will converge, meaning its partial sums, the sequence of partial sums will actually converge to some number. All right, so in summary, what that means for the geometric test is this, that if you have a series, if you know that it is a geometric series. Now, how do I know it's a geometric series? I can memorize these sort of formulas where if it's in this format, this is what a geometric series looks like, AR to the n, or AR to the n minus 1, or AR to the n plus 1. And this can be a little deceiving because it doesn't look exactly like this. So for example, this first series here, what kind of a series is it? Well, when n is equal to 1, this is 3/2 in the first blank. When n is equal to 2, this is 3/4. When n is equal to 3, so 3 is right here, this is going to be 3/8. When n is equal to 4, this is going to be 3/16, and so on. Okay, now this is a series because there's a summation sign here. So I have a plus sign, a plus sign, a plus sign. And the question is, does this sequence of partial sums converge or diverge? And instead of having to add up every single partial sum and looking at its sequence, I can use the geometric series test. And the geometric series test says that if I look at the common ratio between all of these, so what is the common ratio here? 3/2 times what is 3/4? 1/2. 3/4 times what is 3/8? 1/2. My R here is equal to 1/2, okay? And that is less than 1, and I can even say absolute value here to be technical, okay? Then what that means is I can say, therefore, this series converges by the geometric series test, okay? And this is my answer. Technically, you could just say R is equal to 1/2 less than 1 here, but the definition is the absolute value of R. All right, let's look at this problem right here. If I put these into blanks, n equals 1, n equals 2, n equals 3, n equals 4, I need to first verify that it is a geometric series. Not all of our series will be geometric series. If I put in 1 here for n, I'll get 3/2 in the first blank. If I put in 2, I'll get 9/4. If I put in 3, I'll get 27/8, and so on. And so if I kept going on this, let's see, this would be 16, this would be, I guess, 81. So if I kept going on this, what do I see is the R, or is it a geometric series? Okay, well, let's look. To go from here to here, I multiplied by 3 halves. To go from the second term to the third term, I multiplied by 3 halves. And to go from this term to this term, I multiplied by 3 halves. And if you multiply by the same common ratio each time, then what you know is my R here is equal to 3 halves, which is greater than 1. And what does the geometric series test tell me? The geometric series test tells me that if R is greater than 1, then therefore this series diverges by the geometric series test. Okay, so if R is greater than or equal to 1, then the series diverges. If the absolute value of R is less than 1, then this series converges. And then something extra, if the series does converge, I can actually calculate what it converges to. All right, and of all the series you learn, this is the only one that you're going to learn that you can actually calculate what it converges to. This one in the telescoping series, but you're not learning the telescoping series this year. What does this geometric series converge to? Well, it converges to A1 over 1 minus R. Okay, what's my A1? It's whatever's in the first blank, so that's 3 halves over 1 minus, what's my R? 1 half. Make sure this R is less than 1 or else you cannot use this formula. So this is going to be 3 halves over 1 half, which is equal to 3. All right, so if I added this all up to infinity, what would happen is that the series would converge to 3. It does converge, and it converges to 3. All right, let's look at nth term test for divergence. So nth term test for divergence, again, is not on the AP test this year. But it's worth looking at. The nth term test for divergence says if the limit as n goes to infinity of your a sub n is not equal to 0, then this series, okay, diverges. Okay, now the first thing we want to do though is look at the series and make sure it's not a geometric series. Okay, because if it's a geometric series, then what we want to do is just use the geometric series test. That's the easiest thing to do. Okay, but if it's not a geometric series, what we can do is say, all right, I could do the sequence of partial sums, but that takes so much time. All right, let me use the nth term test for divergence to see if this series converges or diverges. Okay, and what this nth term test for divergence says is I take the limit of this, the limit as n goes to infinity of 2n plus 3 over 3n minus 5. So really what I'm doing is taking the sequence and finding the limit of this sequence, okay, seeing what this sequence converges or converges to, or if it diverges, okay. And if when I take the limit of this, I get something that is not equal to 0, okay, so let's see, let me take the limit of this. You know, this is the same thing as if I did the limit as x goes to infinity of 2x plus 3 over 3x minus 5, right? So if I look at this, the x's here, these are the leading terms that have the same power, okay? So this is going to be, the answer is going to be the coefficient of the leading term. So this is 2/3. So this answer here is 2/3, okay? And 2/3 I compare to 0. 2/3 is not equal to 0, okay? So therefore, what I'll say is that this series diverges by nth term test for divergence. Now what's super important here is you add this thing at the end, for divergence. The nth term test for divergence only tells you if it diverges. You would never use nth term test and say that something converges, and that's what students do a lot. Students will say, oh, well, this is equal to 0, so therefore the opposite is true. This series must converge by nth term test for divergence. Okay, no, that's not allowed. Nth term test for divergence is only a divergence test. It never tells you if something converges or not. Okay, and truly you can have this equal to 0 and also have the series converge. All right, so don't switch this around and make it something that it's not. All right, so let's look at this one right here. Again, check to make sure, is it a geometric series? Okay, if it's not a geometric series, then let me try nth term test for divergence. An nth term test for divergence says I take the limit as n goes to infinity of this a sub n, this is the a sub n right here, of n factorial over 2n factorial plus 1. And when I do that, what do I get? Well, you may or may not notice this, but this n factorial here is actually the kind of the leading terms, okay? It has the same power, all right? So another way to say it is when n goes to infinity, this 1 is negligible. So basically what I have is n goes to, the limit as n goes to infinity of n factorial over 2n factorial. What this really is equal to is 1/2. Now what I compare this to, if I'm trying to use the nth term test for divergence, is I compare this to 0. If this is not equal to 0, then I can say, therefore, this series diverges by nth term test for divergence. Remember, it's only a divergence test. I can never say something converges because of the nth term test. All right, let's do another one. Okay, this one right here, let me figure out, is this a geometric series? If it is a geometric series, then I would use a geometric series test. All right, looking at this for a while, don't think it's a geometric series. I can test it if I want, put in some blanks and see if I get a common ratio. But it's not going to be a geometric series. So what I do is I take the limit of this as n goes to infinity of 3n minus 2 over 3n. Okay? And same thing here. As n gets bigger and bigger and bigger, this 2 is going to be negligible. So this is equal to the limit as n goes to infinity of 3n over 3n. And what is that really? Well, that's 1, but you could also say, you know what, these are really the leading terms, and the leading terms have a coefficient of 1 in front of them, so this is equal to 1, which is not equal to 0. Therefore, this whole series right here diverges by nth term test for divergence. And there's something else I'd like to add here, that for nth term test for divergence, if I had a problem like this, let's say problem D, the summation, the square root of n as n equals 1 to infinity, this right here, it's not a geometric series, obviously, so I'm going to try nth term test for divergence to see if the series converges or diverge. If I take the limit of this a sub n, so this is your a sub n here, what I get here, as n gets bigger and bigger and bigger, this will just go to infinity. And you can use nth term test for divergence if you get an answer of infinity. All you do is compare it to 0. This is not equal to 0, so therefore this series diverges by nth term test for divergence. Okay, so you can use this test even if your answer is equal to DNE or infinity. Oh, let's talk a little bit about clarification with n-term test for divergence. Where does this really come from? It really comes from when we were doing integrals a long time ago. So let's look at these two problems. A long time ago, when we did 1 over x, if we graphed 1 over x, do you remember that 1 over x looked like, let's see, it looked like this on this side. Okay, and I'm only going to use the positive sides because this is for, let's say, the integral from 1 to infinity. Okay, and what we said was when I looked to see over here where there was leakage or not, remember I said, let's say this is n equals 1, 2, 3, 4. Okay, if you look at the y values here, they're decreasing and they're going towards 0. Okay, now the question is, does this integral, the area under the curve here, does it converge or diverge from 1 to infinity? So I'm really not looking at to the left of 1 here. I'm just looking at this area right here, okay? Does it converge or diverge? And if I drew the picture for 1 over e sub x, ex, so let's do the same thing. The integral from 1 to infinity of 1 over ex. It actually looked very similar to this picture here, very similar, okay? And if I just wanted the area from 1 to infinity, so that's from 1 here, and then, you know, these are discrete numbers, so n equals 1, then n equals 2, then n equals 3, then n equals 4, and these are your y values as they decrease. So it'd be this y plus this y plus this y plus this y. And as you keep on going, the question is, does this area under the curve converge or diverge? Okay, and if you remember, maybe you do, maybe you don't, okay, what we did was we took the integral from 1 to infinity of 1 over x to see if we got a number here, okay? And remember that that was actually an improper integral, so this was the limit as a goes to infinity of ln of x, the integral of this. Well, let me just take it one step at a time. 1 to a of 1 over x dx, and this was equal to the limit as a goes to infinity of ln of x from 1 to a. And then remember, this is the little brother, okay? You just carry him down, limit as a goes to infinity of, first you plug in the a, then you plug in the 1, then you slap a minus sign in the middle. Now I'm going to plug in the a here. So as a goes to infinity, what I'll get here is infinity minus 0, which is infinity. So this area under the curve, what we know is that it diverges, okay? But if you notice, the limit though of this sequence actually does converge to 0. Okay, it gets smaller and smaller and smaller. However, even though the sequence goes to 0, the sum underneath diverges. If I looked at this problem here, okay, this was the integral from 1 to infinity of 1 over e to the x dx, right? That's the same thing as a limit as, let me do b this time, b goes to infinity of 1 to b e to the negative x dx. That's the limit as b goes to infinity. The antiderivative of e to the negative x is negative e to the negative x from 1 to b. Carry down little brother, so limit as b goes to infinity. This right here is really the same right here. This right here is really the same as negative 1 over e to the x. So let me plug in b there, so it's negative 1 e to the b. Let me plug in a 1 there, so it's negative 1 e to the 1. And then I'm going to slap a minus sign in the middle. So this becomes plus. And then I'll take care of little brother here, the limit. If I put in infinity here, the bottom gets bigger and bigger and bigger. This will go to 0. This will just go to 1 over e. So this integral actually converged, okay, to 1 over e. This area under the curve here converges to 1 over e, which is kind of interesting. What that tells us is this right here is going to diverge, but this right here is going to converge, even though if I took the limit as n goes to infinity of 1 to the n, this would give me 0, right? This gets bigger and bigger. If I took the limit as n goes to infinity of 1 over e to the n, what would this give me? This number would get bigger and bigger and bigger. This would give me 0, okay? So knowing that this limit is equal to 0 tells me nothing about the series, if it diverges or converges, okay? And that's why before, when we talked about this nth term test for divergence, it has to not be equal to 0 for it to tell us anything about this series, if it converges or diverges. If this limit of a sub n is equal to 0, that is not the nth term test for divergence. That doesn't tell us anything. And later on we'll learn some more tests that maybe will help us with this. But just knowing that the limit of the sequence goes to 0 does not tell us anything about whether the series converges or diverges. And hopefully that picture helped you. But if the sequence goes to something other than 0, then this helps us. So this is where the nth term test for divergence helps. Test for divergence is useful here. Okay, this is where it's useful. Okay, not useful here. Not useful. Okay, so if I took the limit of this as n goes to infinity of the square root of n, what do I get? Infinity, right? Okay, well, if the limit as n goes to infinity, as square root of n is equal to infinity, then what I know about the series, this number is not equal to 0. So therefore, this series, square root of n equals 1 to infinity, diverges by nth term test for divergence. And hopefully that made it a little bit more clear to you.